All right, welcome. So my name is Filip, and this is a session about what I think is one of the most fascinating areas in all of science and technology, and that is, of course, quantum computing, and more specifically, the impact that quantum technologies will have on our cybersecurity and our cryptography. So first of all, thank you all for coming. I really appreciate you coming. I really do. I was sort of worried that this is a kind of a niche topic and nobody would come, so thank you. I hope that you will find this somewhat interesting and somewhat useful. You know, there's been a lot of hype in popular media around quantum technologies in recent time, and as it's usually the case, certain things get misrepresented, certain things get taken out of context, they get misunderstood or misquoted. And the goal for this session is to sort of provide you with a little bit more structure to it, and sort of equip you with a high-level technical understanding so that in the future you'll be able to judge the impact of these technologies yourselves. So hopefully this works out. And if you'd like to dive deeper after the session, then I wrote this book that takes you all the way from the basics of quantum mechanics to actually writing quantum algorithms. So I would recommend this book because I really like the author. Now, so let's start with a warm-up question, and I have a lot of stuff that I'd like to cover, so we need to speed up. So this is a warm-up question. I promise you that this is not a tricky question. We will not have to use quantum to actually be able to answer this. So is it possible to have unbreakable encryption? And the answer to this question, I think this is surprising to some people, or maybe many people even. The answer to this question is yes, it is. And in fact, what is even more surprising is that the scheme that guarantees this is incredibly simple. It's the so-called one-time path technique. And the way it works is if you'd like to encrypt your message, you convert it into a binary format, then you generate a random key, and the key has to be at least the same length as the message. And then you go through the individual pairs of bits, so a bit from a message and a bit from a key, and you apply XOR logic between them. And XOR is an exclusive OR, so 0 and 0 would produce a 0. A 1 and a 1 would also produce a 0, but a 0 and a 1 or a 1 and a 0 would produce a 1. And that's it. That is your encrypted message. And in fact, XOR is reversible. So what you can do is you can take the encrypted message, the ciphertext, and you can repeat the same procedure between the ciphertext and the key, and you will be able to recover the original message. Now, if you fulfill certain prerequisites, we can actually mathematically prove that this technique is unbreakable. So these are the prerequisites. So first of all, the key must be at least the length of the message. I mean, that should be clear, right? Because otherwise we don't have enough bits to apply XOR. The second thing is that the key must be completely random. So you really need a very, very good source of entropy to generate your random key. And finally, the key must never be reused. So you can only use the key once for a specific message. So for example, if you have a communication channel based on this, for every single message that travels over the network, you have to keep changing the key. And so if you consider all of that, especially the first one and the last one, it's just not very practical, right? And that is why it's not really used that much. It's used in some places where perfect secrecy is really required. And most famously, I think historically, it was used for communication between the United States and the Soviet Union during the Cold War. They actually had like sheets of pre-generated one-time path keys, and they would use that to encrypt the messages. Now we are going to come back to this one-time path technique at the end of the session, so if I forget, please remind me. But in general, it's just not very practical, right? So we have sort of modern encryption schemes. And we can classify them into symmetric and asymmetric encryption. And symmetric, I mean, one-time path would fall into the symmetric category, means that the same key is used to encrypt a message and to decrypt a message. And now if you'd like to use the symmetric encryption for communication, it really means that the two actors, like in this case Alice and Bob, they have to both have access to the same key, right? Now, the most commonly used algorithm, symmetric encryption algorithm, is AES, Advanced Encryption Standard. In fact, we have so much trust in AES that even NSA allows using it for top secret documentation. Now, symmetric encryption is in general quite fast and relatively easy to implement. But the problem is that if you would like to use symmetric encryption for communication, then you sort of run a little bit into the chicken and egg problem, right? Because if you'd like to use symmetric encryption to establish a communication channel with somebody, a secure communication channel, then both of you have to have access to the same key, which means you have to distribute the key first. And in order to distribute the key, well, you need the secure communication channel, right? And so from that perspective, that is why we also have asymmetric encryption. And asymmetric encryption relies on two keys, right? So there's now not just one shared key, but instead one side of the protocol, so Alice in this case, she has two keys. So there's the first key, there's the second key. And there is actually a mathematical relationship between those keys. So one key is sort of derived from the other, in a way. So there's the private key, and as the name suggests, that is the key that Alice would keep private, and the second key is a public key, and this is what is published and is available to anybody. Now, anybody can take Alice's public key, so for example, Bob can do this, encrypt a message, and produce a ciphertext, but only Alice will be able to decrypt the message because only she has the access to the private key. And so this is also known as public key cryptography, and we also use this for digital signatures. So for example, if you have access tokens, that's basically what they use under the hood, right? So we can issue a token, and then we can sign the token using the private key. And then the public key can be used to verify the authenticity of the token, because then we would know that a token was really signed with a specific private key. Now, we also have models that are actually hybrid. So asymmetric cryptography is not something that we want to do. We only do it out of necessity. So typically what happens is that in most protocols, there is the initial handshake that is asymmetric, and after that we switch to symmetric encryption. So for example, TLS at its core, I mean, this is a little simplified model, but at its core, TLS actually starts with an asymmetric handshake and actually switches to symmetric cryptography, right? So what happens is that if you have a TLS client, like a browser, and you connect to a server over HTTPS, then really the way it plays out is that first you connect to the server, you download the certificate, and at this point you get the public key from the server. Then your client application, so your browser or your application, generates a secret and encrypts that secret using server's public key and sends it back to the server as a ciphertext. And now the server can decrypt it because it has its own private key, and decrypts it, and now the server has the secret as well. So now both client and the server have the same secret, and they can switch to symmetric cryptography, and this is effectively what happens, right? Now, asymmetric cryptography is based on difficult mathematical problems. So this is this relationship between the public key and the private key. And these algorithms are effectively only as strong as difficult those problems are. And the two most commonly used algorithms are RSA and elliptic curves, and they rely on different mathematical problems, and we are going to actually dissect this in the later part of this session. For now, we will just say that there will be impact on all of this through quantum technology. So first of all, we know that quantum computers will be able to break some of the existing established crypto schemes. This is, of course, a huge problem and quite a big threat. So we are going to spend actually most of the session sort of dissecting this. But there are also benefits that quantum technologies will bring. So we know that quantum technologies can be used to distribute keys with what we would say is unconditional security, which effectively means that we could distribute keys in a way that is actually, or the security is guaranteed by the laws of nature. And from that perspective, we might actually reach a stage in the future where we might not need asymmetric encryption at all. So we are going to also look at this. And now the background for this whole session, the context in which this session will play itself out, is this document. It looks not very exciting. It looks like a typical screenshot from your enterprise software. It's actually a screenshot from the United States Congress website. And here at the top it says law, right? There's a date somewhere here, 21st of December, 2022, right? So I was on holidays already at that time, sipping wine and eating cheese, but Joe Biden was really busy because he was signing this into law. So this is the so-called Quantum Computing Cybersecurity Preparedness Act. And this document mandates that the federal agencies of the United States government have to migrate their systems to cryptography that is resistant to quantum attacks, and they have to adopt any other technologies that will help them mitigate quantum attacks. And effectively, you know, the US government is doing this, and as we will see, pretty much everybody will have to start doing this as well. So let's start by talking about quantum threats. And in order to appreciate that, we will have to spend a little bit of time with the quantum theory itself. So what I'm going to do, I'm going to squeeze a year-long university course into about 7 minutes. So I'm sure this will work out great. No, so we know that our information is binary, right? Like in the classical information theory is 0-1 based. This is how we store information, this is how we process information, this is how we reason about information. In quantum information theory, the basic unit of information is a qubit, a quantum bit. And the quantum bit and the bit, they share quite a lot of similarities. Namely, a bit can only be a 0 or a 1. Now, a qubit can only be observed to be in one of two possible states. So from that perspective, it's really the same, right? So we can map one of the so-called observable states to a 0, map the other one to a 1, and we have effectively reconstructed a bit using a qubit. But the major difference between a qubit and a bit is that during a computation, so during the execution of a quantum program on a quantum computer, or more broadly, during the evolution of any quantum system, which is really anything around us, because of course our world is quantum mechanical at its core, a qubit or a quantum object can enter a superposition state. And a superposition means that it is then in a state that is a mixture of both of these observable states. And this has very deep, very profound philosophical consequences, for example. There's the famous paradox of the cat of Erwin Schrödinger that was both dead and alive at the same time, right? So what Schrödinger imagined is he imagined putting a cat in a box. And there was a gun in this box as well. And then the trigger of the gun was connected to a state or to a state of an atom, right? And the atom had two observable states. And if the atom was found to be in one of those states, then the gun would fire. In the other state, the gun would not fire. But as long as the atom was not observed, then it could enter a superposition state, which effectively meant that the gun would both fire and not fire at the same time, which of course then led to a conclusion that the cat was both dead and alive at the same time. Now, again, this has very deep philosophical consequences and leads to a great debate about the true nature of reality itself. But mathematically, it's not really that complicated, actually, because we can visualize the mathematics of a single qubit on what is called the Bloch sphere. It's called a Bloch sphere, but it's really just a sphere, right? So we start at the center, and if I start at the center, and I draw a vector along the z-axis upwards, sort of towards the north pole of the sphere, then this will give me one of the observable states. This is a state that we typically call ket 0. So this is the symbol shown here. This is notation from quantum mechanics. It really just is a shorthand way of expressing that this is a vector. And so this is one of the observable states. Now, if I start at the center and I draw a vector downwards towards the south pole of the Bloch sphere, then this will give me the second observable state. And this is the state that we call ket 1. And of course, these are the two observable states of the qubit, and we can map them to 0 and the 1 to the classical bits. Now you might ask, what would happen if I start at the center and I draw a vector to any other point on the surface of the sphere? And in fact, I can do this. And those are all valid states for the qubit. In fact, I can find infinitely many of such states because I can draw a vector between the center and one of infinitely many points on the surface of the sphere. So this means that a qubit can be in one of infinitely many states, but all those other states can be expressed using this general equation, alpha ket 0 plus beta ket 1. Basically, from the mathematical perspective, this is just a different way of mixing the two vectors representing the two observable states. And all of those other states are superposition states. Now we can only observe these two states, but the qubit can really be in infinitely many other states as well. So superposition is not directly observable, right? Again, this is very important. Now, but how does superposition impact the actual execution of a quantum program? Well, at the high level, if you think about a computer program, it can be really reduced to a sort of a functional approach, right? There is the input, then there is the execution state of a program, and there is the output. And in a classical program, everything is bit-based, right? So we start by inputting some bits into the program. Then the program executes, so there are some bits on top of which it is doing its calculations, maybe in memory, maybe in CPU registry. And ultimately, the program produces some output, and those are also bits as well. Now, in a quantum computer, slightly different. So if we would like to input some information into a quantum computer, we have to create a state ket 0 or ket 1, right? Our information is binary, so if I want to take this binary information and put it into a quantum computer, I have to map it to the qubits. And as we just said, the 0 would map to the state ket 0, and the 1 would map to a state ket 1. So effectively, I've input bits into the quantum computer. But now when the program runs in a quantum computer, each of the qubits in a quantum computer can enter a superposition state. So it can become a mixture of both of the observable states. and this is captured by this letter psi. And finally, if we want to read out something from a quantum computer, as we already said, the superposition is not observable. So the only thing that we can observe are the states ket0 or ket1, which effectively just map to bits, right? So if you look at this now, you can see that the input phase and the output phase is pretty much the same. It's just sort of different encoding of information, effectively. But it's the execution state that is much different, right? Because the qubits in a quantum computer can actually explore the superposition states. And this is the primary advantage for quantum computers. Quantum computers can take algorithmic advantage of the superposition, and this is what we call quantum parallelism. Now, the way you can think about this is a very subtle effect, so you should not read too much into this. But the way you can think about this is if you consider a function f of x, and you'd like to work with this function on a normal computer, well, you'd have to invoke the function many times for different values of x. But on a quantum computer, you can actually create a superposition of all the possible values of x and feed that into the function and try to compute from there. Again, it's a subtle effect, but this is really at the core of how quantum computers work. And we will see how this can be, or how this was used to actually attack our established cryptography. But before we do this, let's introduce this. So one of the most commonly used public-private crypto systems is RSA. It dates back to the 1970s, and the security of RSA relies on the factoring problem of large integers. So this is how RSA works, right? Like, if you'd like to encrypt something with RSA, you start by picking two huge prime numbers, p and q, integers. Then you also pick an exponent e. However, this is a quasi-constant. It's almost always 65,537. And then what you do is you multiply p by q. Once you have done this, you obtain a number n. And what you do is you publish n and you publish e as well. And effectively, n becomes the basis for the public key. So if I would like to now encrypt a message using RSA, what I have to do is I have to use this formula here. And it's actually quite simple, because m is the message. So now I can write any message that I want. I can convert it to a binary. Once I convert it to a binary, I can actually convert it to a number, right? And once I have a numerical representation of my message, I raise it to the power e and calculate modulus with n. And this produces another number, and this is the ciphertext. This is the encrypted message. So effectively, the public key is based on n here. Now, if I want to decrypt it, I use a different formula, which we will not go through, but you can see that both p and q are in that formula. So the private key is effectively p and q. Or to make this simpler, we can say that the security of the whole thing boils down to the fact that if you know n, you will never be able to find p and q. This is how simple it is, right? Of course, now the problem is that n is such a huge number. It's like, it has like 600 digits, for example, for 2048-bit RSA. So that's why it's computationally pretty much impossible, right? Like, we would need millions, maybe billions of computational years to actually factor these numbers and recover the p and q. So here we have a JSON Web Keys document that is published by Google, right? It comes from this URL. So when Google is signing their tokens, Google is using RSA. And then Google is publishing the public keys so that anybody can actually validate the authenticity of a token signed by Google. And you can see they actually publish two keys here, and there is the N, and there is the E here, and this is actually RSA key, right? And so, by the way, this is 65,537, but the N, of course, is unique per key. Now, if I have the computational power to take this N or this N that Google has published, and I was able to actually recover the P and Q out of it, then I will be able to actually sign tokens as if I was Google. So I will be able to actually impersonate any Google user, which of course would be a disaster for Google. However, if I had the computational power to recover the P and Q for an N in RSA, then I probably have more interesting things to attack than Google, right? Like, I would probably go to a bank first. But in principle, the security of the whole internet and all of our communications is underpinned by asymmetric cryptography, like RSA in this case. Now, in 1994, Peter Shor published this paper, which is one of the most important papers in the history of computer science, also in the history of quantum computing science, and also more broadly in the history of quantum physics. In this paper, he showed that on a quantum computer, you can actually achieve exponential speedup when it comes to factoring integers, so basically finding p and q for the n. And of course, exponential speedup, I mean, is a huge speedup, right? Like, So that was quite remarkable, because at that time there were no quantum computers at all, right? They were purely theoretical devices. So this was a theoretical algorithm for a theoretical device. And of course now we do have quantum computers. They are still quite small, and they make a lot of errors, and they are not very stable, and they don't have high fidelity. So we are still very far from being able to efficiently run Shor's algorithm, but there's a really quick progress in the field, right? So how would you attack RSA? Well, you do this by following these 3 steps that basically Shor developed. So you pick a number that is smaller than n. It has to be a coprime with n. But so you pick a number a, and then you consider a function that looks like this. So a, so the number that you have picked, to the power x, for many different x's, of course, and then modulus with n. So this is then the function that you're trying to, or this is the number that you're trying to factor. And if you plot this function for many different x's, you would actually recognize that the function starts to repeat itself. So there's this repetition interval in the function. And that repetition interval is effectively what we call the period of the function. And once you have found the period of the function, you can actually calculate the candidates for P and Q using the greatest common divisor algorithm, which is the algorithm that we have known since ancient Greece. So this is not a problem. So in fact, this second step is where it's pretty much impossible for normal computers to solve this, but it's efficient, or very efficient, to do this on a quantum computer. So here's an example of attacking 4-bit RSA, right? So we are factoring number 15. So we are going to set a to 13. This is randomly chosen. It's just smaller, and it's a coprime. And then we are going to plot the function. In this case, it's 13 to the power x modulus 15. And you can see, I've already plotted this function. You can see that it repeats itself at intervals of 4, which means that the order of this function is 4. So we have found the order of the function, and we can then use the formulas from the previous slide to actually calculate the P and Q is 5 and 3, which is correct because, of course, 5 multiplied by 3 is 15, right? So now if you have 4-bit security, like 4-bit RSA security anywhere, then you should immediately leave this session and go home and update your systems, because we have just broken it. But of course, for sufficiently large numbers, it becomes impossible. And now what Peter Shor realized is that he can use a technique called quantum Fourier transform, which is effectively a quantum variant of the fast Fourier transform algorithm that is commonly used in many different branches of mathematics and also computer science, for example, in digital signal processing. And by computing in the superposition, he realized that he can find the order of the function efficiently. Now, this is a bit out of scope for this session, but this picture here shows the so-called quantum circuit for implementing Shor's algorithm. And each horizontal line here, that actually represents a qubit in a quantum computer. And this might not be visible, but they all start in a state ket 0. But then the first thing that happens to them is this H transformation. And the H transformation in a quantum computer places a qubit into a superposition state. So effectively, we are now creating this huge superposition of all the possible values, so all the possible qubits here. And this is like the entry point into the algorithm. So going deeper is sort of out of scope for this session, but I wanted to highlight this because it really ties this into our discussion about superposition, right? Now you might say, but this is RSA, and RSA is sort of quasi-legacy. Like in TLS, we have better algorithms, like we are using elliptic curve cryptography. And that is actually true. So we are using elliptic curve cryptography a lot more now in TLS, especially like in TLS 1.3. It's not even possible to use RSA for key exchange. But there are different reasons why we want to use elliptic curve cryptography. It has smaller keys. We can rotate those keys much more easily. We can use the so-called ephemeral keys. But in principle, against quantum computers, it doesn't really matter, because Shor's algorithm can also be used to attack elliptic curve cryptography. And in fact, there was a paper a few years ago from Microsoft where they showed that in order to attack elliptic curve cryptography, you actually need only about half as many quantum computational resources as to attack a similar size RSA. So from that perspective, it doesn't really offer much protection against quantum computers. So now the important question is how likely it is that we will be able to run Shor's algorithm anytime soon. So the Global Risk Institute in Canada, they do this periodical survey of the top quantum computing scientists in the world. And I asked them different questions, and one of them is when RSA will be broken, right, in a reasonable amount of time. And so these are the answers that they gave in the last year's edition. So you can see that there's still quite some time, right? Like about half of the people, or the scientists that were surveyed, they believe that this will happen in 15 years, and then pretty much everybody agreed that it will happen in 30 years. So it sounds like we have a lot of time, right? Like, what are we even doing talking about this today in 2023 on a Wednesday in Porto? I mean, yeah, it seems like there's a lot of time, but the reality is that in many ways it's already too late. Because if you imagine the threat actor, especially the state threat actor, without pointing which state, right? So a state threat, what they could be doing already now, they can just be capturing all the HTTPS traffic. They can be capturing all your messages that you are sending over the internet. And they're just going to put them into storage. And in 20 years or 25 years, when they have a quantum computer, they can just decrypt all of that and see everything, right? So from that perspective, it's already too late. And that is why it's important to move to post-quantum cryptography. Now, we are going to talk about this in a moment, but before we get there, is asymmetric cryptography the only thing affected by quantum computers? The answer is no. So symmetric cryptography as well, however, there we are not so much worried. So in 1996, Love Grover of Bell Labs published this paper in which he showed that you can have a search algorithm, unsorted, or search through an unsorted data set running on a quantum computer that achieves a quadratic speedup over the best known classical counterpart. So what does it mean? So imagine that you are trying to find a number in a 4-bit data set. So it's a number between 0 and 15, right? And let's say you are trying to find the number 3, but the data set is unsorted, right? So you don't really have a pattern to use. So the best thing you can do is just to look randomly, and statistically speaking, after 8 attempts, you'll find the correct value. Now, on a quantum computer, because of Grover's algorithm, there's this quadratic speedup that you have. And so you will actually find the number in a square root of 8, which is about 2.8. And this diagram shows the so-called Grover iterations. So basically, between the second and the third step, you can see that there is pretty much 100% probability that you find the correct value. So this is mightily impressive, right? Because if you have something that needs 100 steps on a normal computer, it needs 10 steps on a quantum computer. And the same technique can be used to attack symmetric cryptography. But we are not worried because it's only a quadratic speedup, it's not exponential. And therefore, we can simply increase the key sizes. So by doubling the key sizes for symmetric encryption, we completely offset the disadvantage of quantum computers. So that is why we are not worried about symmetric encryption. So let's summarize everything that we talked about, right? So we talked about symmetric and asymmetric encryption. The most popular algorithms are AES for symmetric, and then RSA and elliptic curves for asymmetric encryption. They come with different key sizes because that is the nature of how the algorithms are implemented, right? And then each of those key sizes, then it leads to certain effective strength, which we want to have over 100 bits effective strength, right? Now, if we want to calculate the effective strength against quantum computers for symmetric algorithms, because of Grover's algorithm, we have to consider that to be half of what it used to be. So for example, 128-bit RSA, 128-bit AES, it's effectively 64-bit strength, which is something that it's too low for us. Now for asymmetric, however, and this is not so great, we should consider all of them to be vulnerable, right? So we don't have internet. It's back to the communication like we had it in the beginning of the 20th century. And so this is a great concern. So in 2016, the National Institute of Standards and Technology in the US, they announced a competition for post-quantum cryptography. So the goal was to develop asymmetric encryption that would not be vulnerable to quantum attacks. And last year, they published a set of winners. And so these are the algorithms that have been chosen. Kyber, Dilithium, Falcon, and Sphinx Plus. Now, only one of them, Kyber, is actually suitable for key exchange, so can be used to be embedded into TLS to really perform the handshake. The other 3 algorithms, Dilithium, Falcon, and Sphinx Plus, they are actually signature algorithms, so they can be used for signature generation. Now, Kyber and Dilithium have been chosen as sort of de facto standards, like general purpose use, right? Falcon has been chosen to be used in places where applications need smaller signature size, And then Sphinx Plus is a sort of a backup algorithm because it actually uses different mathematics under the hood. So all these three, they are based on the area of mathematics called lattices, so effectively on vector problems in the lattice space. And at the high level, because we talked about the mathematics of RSA, I just wanted, for the sake of completeness, I wanted to include this very simplified picture of how Kyber and Dilithium work. So this is a concept called learning with errors. And basically, what Kyber and Dilithium do is you start by selecting two vectors in this lattice space. So this is like highly dimensional grid, effectively. So you select two vectors, highly dimensional vectors. And then you calculate the inner product between them, which gives you a number. You divide this by a certain modulus, and then you introduce an intentional error, and this is the key part here. And what you get is you get a number that you can publish. And in fact, what you do is you publish the t here, you publish one of the vectors, and you publish the q. But the s and the error you keep secret. And effectively, the security of the whole thing comes down to the fact that computing t in this equation is very, very easy. But if you know the t and you know the a and the q, you will never be able to find the s, which is needed to do, for example, the signing with private key. You'll never be able to find it, and the reason why you cannot find it is because of this intentional error that was introduced. Again, this is just a high level, so yeah. And so this is now being standardized, right? Both Kyber and Dilithium are being standardized, so there are drafts that have been started in March this year. So there is actually a draft for how to do a TLS handshake with TLS 1.3 using Kyber. Actually, it's a hybrid agreement, so it does like double encryption, also using classical. And there's also a draft on how to use Dilithium with JSON web tokens and JSON web keys and so on for inclusion in access tokens, for example. So these are still drafts, but they are being now included and rolled out into different products. So for example, Google Chrome now supports this draft, and you can do a TLS 1.3 Kyber-based key exchange by enabling a flag in Chrome. Now, Cloudflare, they actually rolled out already last year, they rolled out post-quantum cryptography support for TLS 1.3 on all of its endpoints. So actually what we can do, I wanted to show this. So here I'm in Chrome. So I'm in Chrome 1.18, which is the latest. And you can see that I have this TLS 1.3 hybridized Kyber support, so you can enable this. And once you have enabled this, I can go to Cloudflare. And now what we can do is look at the network tab, or the security tab. And notice what happened. It says I'm using TLS 1.3, and the handshake was done using Kyber, right? So you have this already there, which is quite cool. And Cloudflare is now rolling this out for all the customers as well. So previously they had that on their own services. But now if you are hosting something with Cloudflare, you will automatically get post-quantum cryptography in TLS 1.3 just like that. So that is quite nice. Now just last month, Signal announced that they also moved to post-quantum cryptography based on Kyber. So the handshake, when you are using Signal for messaging, then this is based on Kyber now as well. So that's quite cool. And in general, post-quantum cryptography has now implementations in all major programming languages, right? So I'm going to show a demo in a moment with .NET. And for .NET, it's available through the Bouncy Castle cryptography project. So we are going to have a look at this in a moment. But before we do, I briefly wanted to also mention this, the Open Quantum Safe, which is a project from the University of Waterloo. And what they do is they provide implementation for post-quantum algorithms in C. And there's like a C library that they are building. I think it's called Leap OQS. And so they build this C library, and because it's C and it's built for all the targets, you can use it really everywhere. And so that is quite nice, because then you can embed it into any device or any platform that you'd like to do post-quantum cryptography on. And another thing is that they also maintain forks of both Boring SSL and OpenSSL 1.1.1, where they actually integrated post-quantum cryptography into those libraries as well. And because, especially with OpenSSL, it really underpins most of the security online and also in many mobile devices, so you can embed it into your own applications this way. And for OpenSSL 3, there is a different model of plugging in custom cryptography. So this is provider model, so they don't need to fork anymore. They actually have a provider that you can just install, and that works with OpenSSL 3. So with that said, let's have a look at some code. Is this large enough? Yeah. No? How do I make this larger? Here. Like this. Yeah. But don't worry, I have this secret zoom here, so I can also use that. So I have here, this is a .NET 7 application. This is just a console application, right? It's nothing special. But what I'm referencing here is this bouncy castle cryptography. So this is the project that that brings Kyber and Dilithium support for .NET. Actually, I now think maybe we can switch to a different team, but I'm not sure how to do this in Rider. Which one is light? This one is better. Yeah. So I have two examples here, and one of them will be a Kyber example, and the other will be a Dilithium example. So let's start with Dilithium. So what we need is the data that with Dilithium we can actually generate a signature, right? So we are going to start by grabbing some data from the console, and we will convert it to a byte array. And then we are effectively going to initialize Dilithium. And in order to do this, we need a random number generator, and we also need to tell Dilithium effectively which parameter set to use. So Dilithium 3 is like this mid-level recommended security level. And once we have Dilithium initialized, we can generate the public and the private key. And once we have the public and the private key, we are going to print them to the console just so that we see them. And with the public key, we will be able to verify the signature. With the private key, we will be able to generate the signature. So we create a Dilithium signer, we pass in the private key, and we can then generate the signature over our data. And this is the signature. And now I can also initialize a second signer, and this time I'm initializing it with the public key. And this time, because it's initialized with the public key, it can be used for signature verification. And so that's what I can do. I can say, here's the data, here's the signature, and is the signature correct? And that's basically this, right? So we can run this. And I'm going to say Dilithium. So we can say it's just some message, hello Porto, and this is basically what it prints out. So we have the public key and the private key that were created by Dilithium. They are, of course, different. They are much longer than that, but they are truncated so that they wouldn't cover the whole screen. This is the signature, and then the verification succeeded, right? So what we can also do is we can have a look at Kyber, right? So if you now squint your eyes, we are going to effectively be doing the same thing that happens inside of a TLS during the TLS handshake. So we are going to start by setting up Kyber. This is similar to setting up Dilithium. We need a random number generator, and we need the parameter level for Kyber. So again, Kyber 768 is like this mid-level security. You can see that there are different ones to choose from. So this is the one that is generally recommended. Now, we generate then a key pair, and I will now refer to it as Alice, because this will help us imagine that we really have two actors here, right? So now Alice has a public key, and she has a private key. And of course, the private key she keeps private, but her public key is something that can be used by others, so now by Bob. And you can see that Bob is going to use the public key of Alice to generate a secret. And Bob will now have a secret that will be encrypted using Alice's public key. Right? So this is this built into Kyber, this procedure. But effectively, what happened is that Bob produced a random secret that he keeps for himself, and that secret is encrypted using Alice's public key and can travel back to her as a ciphertext. And so that travels back to Alice, and she can use that ciphertext and use her own private key to actually extract the secret out of the ciphertext. And of course, the secret of Alice and the secret of Bob at this stage, they should be identical, and that is actually checked at the end of this procedure. So again, this resembles at the high level a TLS handshake, right? So we're going to say Kyber, and look what happens. So we start by, we start with Alice, and Alice generates a public key and a private key. They are different, of course. Then Bob produced a secret, and then that secret was encrypted using Alice's public key. And this produces this ciphertext, which then travels back to Alice, and she uses her private key to extract the secret again, and we can already see that these secrets are equal. So at this point, they can actually switch to symmetric cryptography. So how would you actually integrate something like this into your own applications? So one example is to integrate this into an identity server, right? Like if you have done any work with ASP.NET Core and OpenID Connect or OAuth 2, you have surely used identity server. It's now called Duende Identity Server. And so this is an OpenID Connect server that can be used to issue tokens, right? So for that, I've created a small package that acts really as a bridge between identity server and bouncy castle cryptography that allows me to actually use dilithium keys within identity server as valid source or valid credential for signing tokens, right? And this is done here. And so this is a regular bootstrapping procedure for the identity server. In fact, I generated this example from the quick start that identity server provides. The only thing that is special here is that I am actually adding here a dilithium signing credential, right? So I'm saying, please sign the tokens using dilithium. And in this case, the dilithium key is read from the file system, so I have it serialized to a file system. But there are many other things that you could do. You could read it from the key vault, you could generate it on the fly, you could even have identity server manage this for you through this library that I have mentioned. And once we have this in place, I can run the identity server, and I can call an endpoint that is called well-known OpenID connection JSON web keys, right? So this is defined by the OpenID specification, how you should retrieve public keys from an identity server. And if I now call this endpoint, it now responds with a single key, so there is only one here. And this key is using the algorithm Crystal's dilithium 3, right? So this shorthand name, this is actually defined by one of these draft specifications that we briefly mentioned. And so if I now fetch a token from this identity server, which I'm doing now here using a normal client credentials flow, that's part of OAuth 2. So I can fetch a token, and you can see that the token comes back. And if I copy this token, copy, and I paste it over here to have it decoded, you can see that the token contains the normal claims that you'd expect in a token, like scope and audience and so on. But in the header, it actually says that the algorithm that was used to sign this token is Crystal's dilithium 3. And the key, of course, here is matching the key that identity server is publishing over here, right? This is this key here. So this information here in the header, that is the indication for the application that will be consuming this token, how this token should be validated. So from where to get the public key, and also what is the algorithm used. So the final piece for this would be to actually have an API that is able to consume such a token, right? So I have here a pretty standard ASP.NET Core web application. In fact, it doesn't have any dependencies other than this one package that is like a sibling package to the one that I use to issue the tokens, right? So this is the one that will help me validate the tokens. And in the application setup, I'm using the regular ASP.NET Core security. So this is all standard stuff in ASP.NET Core. I'm plugging in the JSON Web Token Bearer middleware. And there's this one additional line here only, oh, by the way, please configure the dilithium token support. If this was not here, and I try to call this API with a token that was signed using dilithium, it would just throw, because ASP.NET Core out of the box only supports the cryptography that is out of the box supported by .NET, which of course dilithium is not at this stage. So by having this in place, I can run the API, and I can call it with my own token, right? This dilithium token. So just to show you that I'm not cheating, I will call it without the token first, and it will come back with a 401, right? And as soon as I pass the token using the bearer scheme, so this is a token that is coming from this other tab in Postman. and it now responds with the hello world, right? So it has successfully validated the token. So this call here, I mean, it plugs a little bit of machinery behind the scenes. It knows how to retrieve the Dilithium public keys and so on. But it's all pretty much plug and play in terms of usage. And in this case, the Dilithium algorithm is like a one-to-one replacement for using RSA-based algorithms, which are not normally typically used. Okay, so we talked about quantum threats. So let's finish off this session by talking about the benefits of that we will have from quantum technologies. And in order to appreciate that, we have to introduce a different basis. So far we were only talking about the states ket0 and ket1. And they together, they form the so-called Z basis because they are aligned with the Z axis through the Bloch sphere. However, there's nothing in quantum mechanics that forces us to use the states ket0 and ket1 when working with a qubit. In fact, quantum mechanics only tells us you only can have two observable states at once, but doesn't tell us which states this should be. And in fact, mathematically speaking, any two points that we find opposite from each other on the Bloch sphere, the so-called antipodal points, can be connected with the center of the sphere using vectors, and they would form a valid basis. And effectively, a basis is, again, it's a pair of observable states. So the basis that is very often used is this X basis, because it aligns with the X axis through the center of the Bloch sphere. And it consists of the states that are typically called ket plus and ket minus. Now, we cannot call these states ket0 or ket1 because they are mathematically different. So the vector is different because the mathematics is like flipped on its side now, right? But in this case, these states become the observable states in a qubit, and the states ket0 and ket1 are no longer observable. Because we still have only two observable states, we have to map them to bit 0 and bit 1, of course. And the concept of the superposition is still there, right? So every other state except this ket plus and ket minus, that is a superposition state, including the state ket0 and ket1, which previously were observable, now they are not, because we can only observe now ket plus and ket minus. If this doesn't make sense, then the way you can think about this is that the choice of basis is a different way of encoding and decoding information in and out of qubits. So we can encode a 0 into a qubit by creating a state ket0 or by creating a state ket plus. And we can encode a 1 into a qubit by creating a state ket1 or ket minus, right? And if we put them side by side, something very interesting emerges. Because if you consider a state ket0 like this, right? If we have a qubit that is really in a state ket0, and I try to observe this qubit using the Z basis, then I will get a deterministic result. Because the qubit will always tell me that, yes, thank you for observing me, I am really in state ket0, right? But if the qubit is in a state ket0, and I try to observe it using the X basis, well, this is a state that is impossible to be observed in the X basis. It's a superposition state. So what I will get as a result of such an observation, I can only get ket plus or ket minus. These are the only two things that are observable. So what I will get is a random result. I will randomly get this or that, right? And not only that, the way you can picture this is that if the arrow was pointing here upwards, then by observing the qubit in the wrong basis, effectively the arrow moves to one of the observable states, either ket plus or ket minus. So not only we got a random result, we destroyed the original state. And this is the key thing here. If we observe in the wrong basis, we are going to destroy information, right? And this is very, very powerful concept because the choice of bases in a qubit allows us to encode information in a very specific way. You will only be able to read this information if you know the encoding that was used in the first place. If you don't, you will not only get the random result, you will destroy the information. And it's like security that is built into the very fabric of our reality. You have one shot at reading the information, and if you choose the wrong basis, you will destroy the information. And this is something that we call entropic uncertainty relation, and this is really at the heart of quantum cryptography. And there's another interesting consequence of that, and that is, if you don't know the encoding of a qubit, you will not be able to make a copy of it. Now, there's a beautiful mathematical proof for that, but just using common sense, what is the act of copying? If I have something here, and I'd like to copy it over here, what do I have to do? Well, I have to take the source thing and accumulate all the possible information about this thing, and use that information to reconstruct this thing at the target location. But with a qubit, in order to get any information about the qubit, I have to observe it. But I cannot observe it if I don't know the basis, because otherwise I will destroy it, right? So from that perspective, it's impossible. And in 1984, Charlie Bennett and Gilles Brassard published a paper that used exactly this principle to develop the first quantum key distribution protocol. And with a quantum key distribution, what we can do is we can actually exchange a secret in a secure way over a channel that is insecure. And this is like, I mean, this is just not logical, it's not a logical statement, but this is thanks to this effect that we just discussed. So here's how it works. So Alice generates a long sequence of random bits, and if she wants to establish a 256-bit key with Bob, she will have to generate 4 times as many bits, so she has to generate 1024 random bits. We will see in a moment why this is the case. She then proceeds to encode those into qubits by randomly switching between the Z and the X bases. So a 0 in the Z basis, state cat 0. A 0 in the X basis, state cat plus, and so on, right? 2 different bits, but 4 different quantum states. She then sends those qubits over a quantum communication network, some sort of an optical link, for example, to Bob. And this channel doesn't have to be secure, so they don't have to have a sort of a TLS connection here, right? And then Bob proceeds to decode those qubits. But he doesn't know how to decode them because he doesn't know which bases Alice chose. So what he does is he also randomly switches between the Z and the X bases. And next thing, Alice and Bob communicate over a public channel and compare the bases that they use. They keep the values secret, just the bases. And they throw away all the values for which they used incompatible bases. But for where they use the same bases to encode and decode a bit in and out of qubit, they should now have the same bit value, right? So they should now have a shared key in their possession. Now, statistically speaking, because there are 2 bases, Bob will be correct in about half of the cases. So they would throw away half of the bits and half of the bits are left. So if they started with 1024, they are now down to 512, right? So they have to make sure that there was no eavesdropper on this communication channel, because we said that this channel is insecure. But as it turns out, the attacker is very limited in terms of what the attacker could do here, because the only thing that the attacker can do is to try to copy the qubits. But to copy the qubits, the attacker has to observe them. But if the attacker doesn't know the encoding bases, well, the attacker cannot make a copy, right? This is forbidden by the laws of quantum mechanics. So the only thing the attacker can do is to also guess the bases, right? And that would inevitably destroy some of the original information that Alice encoded. So what Alice and Bob can then do is they take half of the remaining bits. So they had 512, so now they take 256 bits. They reveal them to each other. And if they find any mismatches, it means that there was an eavesdropper that actually destroyed some of the original information that Alice encoded. And that's how they can detect an attacker. So in other words, they are always able to know if somebody read that information. And this is tremendously powerful, right? And it all sounds like science fiction, but it's actually not. And there are products on the market that use just that. For example, there is a company called ID Quantic in Geneva. They've been building solutions for quantum key distribution for over 15 years now. They've been supplying this mostly to government entities. In Switzerland, they've been securing local elections, for example, in Geneva with this. Last year, they deployed the world's 2nd largest quantum key distribution network for the government of Korea. They connected, I think, 48 locations in Korea with this network. And now here's something else. We started this session by talking about the one-time path technique. And one-time path technique, we know that the encryption it provides is mathematically unbreakable. Now, it doesn't tell us how to distribute the key. And this is the opposite. It tells us, here's a way to distribute the key in a way where the security is guaranteed by the laws of nature. It doesn't tell you anything about encryption. It just tells you once you have a symmetric key, you can use whatever encryption you want. And if you bring the two together, you can really have end-to-end perfect security, right? That is mathematically verifiable. And of course, for extreme cases, this is something that we would definitely want. And the final thing that I wanted to mention is this. So Chinese researchers, they actually have a low orbit quantum satellite, and they are able to run this protocol, quantum key distribution protocol, through or between a ground station and a satellite, or using the satellite as a repeater between the 2 ground stations. And this is sort of like a sneak peek into how we think in the future quantum internet will work, right? Because quantum internet will definitely have quantum key distribution at its core for security. Yeah, I think that's it. So this is everything that I wanted to talk about. If you'd like to see those slides, they are online. They are just a web page, so they can be viewed in the browser. The demos are here. There's actually more demos there. If you are interested in quantum computing in general, there is a demo there of Grover's algorithm, also Shor's algorithm. There's the quantum key distribution demo as well, and all kinds of stuff. If you visit this page in the browser, you can click here, which will very conveniently take you to a shop where you can buy a book. And all the photos, so this is actually something that I always like. So the photos here, all the photos, the backgrounds, they come from CERN, from their public outreach program. I think I wasted all the time, so I'm not sure we have time for questions, but what I would suggest to do is that if you'd like to talk about any of these topics, just grab me afterwards. It's anyway better to talk sort of in a more private fashion. And thank you for coming. I also have one copy of my book that I'd like to give away. So if somebody wants it, just the first person that wants it, then you can have it. Thank you so much. It's here. It's real. It's not an e-book. It's a dead tree. Thank you so much.